Hey, everybody. Welcome to our webinar today on tankless gas water heaters, the infamous methane puff. We hope you all are doing well and starting off to a great 2023. I want to say thank you to our artist, Barb Burwell, for creating this great image that you see on our screen of these tankless gas water heaters emitting their methane puffs. I'm Joe Wachunas from New Buildings Institute and Electrify Now. I'm here with Brian Stewart from Electrify Now. We're really excited about today's webinar. And we'll introduce our panelists in just a second. Great. If this is your first time on an Electrify Now webinar, we are an all-volunteer organization that believes that electrification is the quickest way to decarbonization. We boil that into 4 easy steps. Number 1, clean up your electric supply through community solar or rooftop solar panels. Number 2, electrify your home. We've got lots of great ways and tips for doing that on our website, electrifynow.net, or our YouTube page. Just Google Electrify Now YouTube. Number 3, electrify your ride, be that a bike or a vehicle. And then number 4 is electrify everyone, expanding the benefits of electrification to communities that need them most. And Brian, tell us a little bit about who we are fundraising for this year in 2023.
Yeah, well, you've heard a lot of us talking about our water heater program. We're still working on that, but we also are working with a group called Seeds for the Soul, another local group here in Oregon, and they have this great funding program that they've set up for many years now, where they're able to supply gap funding for low-income families to put rooftop solar on their homes with no upfront costs. And then they do this, one of their main mechanisms are these zero-interest loans that they provide to those families so that they can repay that amount of money that they needed to do this through the savings that they get on their electric bills. And so over a few years, they pay these low interest or zero interest loans back. And then after they've paid them off, they're getting huge savings on their energy bills. So Seeds for the Soul has installed over 130 of these in Oregon so far, and adds up to about 500 kilowatts of energy that's installed in over almost 450 tons of carbon that's avoided every year through this program. So we love this, and we appreciate your donations to help make their program even more robust.
Yeah, we're so excited to partner with Seeds for the Soul. I put a link to Seeds for the Soul in the chat. I also opened up the chat to everyone. And so if you want to put where you're coming in from today, we always love to hear where people are listening in from. Quick shout out to our Electrify Coalition. This is over 50 organizations that believe in the mission of electrification, from trades to nonprofits to utilities and interested partners. So we want to say thank you to everyone who's interested, who's joined the Electrify Coalition. It doesn't cost anything. Email Brian or I if you're interested in joining, and you can find our emails on electrifynow.net. Okay, let's dive into our webinar today. Brian, why are we talking about tankless gas water heaters?
All right, well, I think it's good to start with just a big picture view about water heating and acknowledging how much energy it takes and how much of a household energy budget is consumed by water heating. Of course, these numbers will vary a little bit from around the country. You know, we see something like 15 to 17 at the low end, and as high as 30 or 35% at the high end. Here in Oregon, the Department of Energy says it's 30% of a typical residential energy consumption per year. So it's a huge portion. And anything we can do to reduce that obviously is good. But really what we need to do is figure out how to eliminate that energy, the carbon emissions from that energy. There's 2 major sources or technologies that are typically used for water heating, and these are the common ones: electric storage and gas storage. These are the ones that most people are familiar with. They've been around for a long time. Each of them here in the Northwest is roughly 50% of the market share. But there are these other devices that you see, gas tankless, which we'll be talking about, of course, and why. Electric tankless, this is less popular even than gas tankless, but here, for example, in the studio here, we have an electric tankless because we use such little amounts of hot water. It's a good solution, but for most people, it's not a popular solution. Then, of course, there's electric heat pumps that are relatively new. They've been around for around 10 years. We're going to talk more about them later. But these are the 5 basic technologies. There is also rooftop solar water heating, and that's usually in combination with either a gas or an electric storage backup unit. We're not going to talk too much about that. And those are less popular now that electric heat pumps have come along and do a lot of the same thing and easier to install. So these are the major technologies. But the reason why we're focusing on gas tankless is because, one, they have this reputation as being a kind of green solution. We'll talk more about that later. And maybe because of that, their sales have been increasing pretty dramatically over the last 10 years. So we really want to make sure people understand everything that's involved with this gas tankless. And I think actually when we hear about from our panelists here, you'll understand that these things, it's a little bit more complicated than this story of them just being more efficient. So that's why we're diving into gas tankless water heaters, to really understand, first of all, what they are and how they work, why it enjoys this reputation as an environmental solution. And then, of course, there's the whole methane puff thing. I mean, what's the story with methane leakage? Because there's just so much more data available now about how all gas appliances leak. And we've got one of the national leaders in that with us today. We'll be introducing momentarily. And so this leakage really changes the picture for how these things operate and their total emissions picture. And so we'll talk about how these technologies compare. Gas tankless compares to other technologies for efficiency and cost and operating costs and carbon emissions. And then we're going to end with a little bit of just a sneak peek on what's coming with some of the latest water heater developments that we're aware of. So with that, I want to turn it over to our guest panelists today. We're really fortunate to have Dr. Eric Lebel with us. He's a research scientist at PSC Healthy Energy. His research focuses on emissions of methane and other health-damaging air pollutants in California. And specifically, he studies abandoned oil and gas wells, but also residential appliances. And he's developed these new methods to systematically quantify the methane emissions and other pollutant emissions that come from these sources. He was a graduate from Stanford University with a PhD in environmental earth system science. And he began focusing on methane emissions for his research there. So a lot of the work that you're going to see is building on what he started there. So with that, I'm going to turn it over to Dr. Lebel and take it away.
And Eric, while you're loading up your slides, I'll encourage folks to put any questions into the Q&A. That's easier to track, and then leave the chat for comments. Thanks so much.
All right. Thank you so much for having me. Can you see the slides okay?
Yeah.
Perfect. Yeah, so thanks, Brian and Joe. I'm happy to talk today about my work on methane emissions from natural gas water heaters. And as they said, that this is work that I completed while I was doing my PhD at Stanford University. And this paper has been published in Environmental Science and Technology, and is available online if you want to read the details in more detail, or read the paper in more details after the presentation. But I thought we could start by first talking a bit more about methane emissions in general and why we care about them. Methane, as many of you probably know, is the second most important greenhouse gas after carbon dioxide. And like carbon dioxide, it's been increasing very rapidly in the atmosphere over the past several decades. In particular, we've now more than doubled the methane concentration in the atmosphere from pre-industrial times, and it's continuing to rise. In part because of the emissions from oil and gas, and particularly from the water heaters, which we'll talk more about later, as being one of the components of methane emissions. But just to give a better understanding of where methane comes from in the atmosphere, here's a diagram of several sources of methane emissions published by the Global Carbon Project. And you can see that we'll talk mainly today about this block here, which is where the water heaters and other gas appliances fit in, which is fossil fuel production and use. But agriculture and waste, another anthropogenic major source of methane emissions. Biomass and biofuel burning is another source of methane emissions. And then there's some natural sources of methane emissions, which are wetlands, and then others, emissions from inland waters, geological, oceans, etc. And then, of course, there are sinks in the atmosphere as well. Mainly, methane is removed from the atmosphere from chemical reactions, and it can also be removed from the atmosphere from soils. But today, I'd like to talk mainly about the fossil fuel industry, and particularly where methane emissions come from in the fossil fuel industry. What we know, there's been a lot of research on upstream methane emissions, mainly from drilling, fracturing, production, processing, transportation, and distribution. We know that methane can leak from any one of these supply and distribution chain components. And methane is just, it's a gas, and so anywhere that there's a leak in the system, the methane is emitted, and many times it's leaked unnoticed. End use is another particular possible source of methane emissions, and until recently, there hasn't been very much research that's been done to understand how much methane is emitted from homes and buildings, for instance. So that's what is part of my PhD dissertation, was trying to understand how much methane is emitted from different appliances that are commonly used in residential homes. And so one of those appliances, of course, is water heaters. So that's what we started the project, was looking at the difference in methane emissions between tankless and storage water heaters. But before talking more about that, I just thought we could first understand how the gas is used in a residential home. So most gas in a typical home is used for space heating. The second most highest use is water heating, and cooking and other uses make up a very small chunk of the pie. Other uses would be appliances like gas fireplaces, clothes dryers, pool heaters, etc. It's particularly in warmer climates, the space heating may be a bit less of the pie, and the water heating would be a bit more, depending on the heating demand for the climate that the house is in. But it's important to know that the space heating and water heating in most cases make up the vast majority of the gas use in a home. But interestingly, the number of appliances in a home is much more evenly distributed. So you can see here that when you look at the number of appliances, not how much gas they use, you can see that most people, if they have gas in their home, will have space heating and water heating. So this is a furnace and a water heater. And many of them will also have a gas stove as well. Other appliances, so this would be the fireplaces and clothes dryers, are also pretty common, although they don't use very much gas compared to space heating and water heating uses. In total in the US, there's 188.9 million gas appliances as reported by the EIA's Residential Energy Consumption Survey. So today I'm going to talk more about the natural gas water heaters. So this is a picture of commonly what we're going to refer to as a storage water heater. Some people also will call them tanked water heaters. And then this is a tankless water heater. The main difference between the two types of water heaters is that the storage water heater will heat the water inside the tank. They're usually anywhere between 40, 50, 60 gallons, and it will keep the hot water hot in that tank at that temperature until it's needed, in which it will be drawn out of the tank from the hot water pipe and pumped into the house for the use at where the water is being drawn from. But in converse, the tankless water heater will heat the water on demand. So these are also sometimes known as on-demand water heaters. And so the way that works is that anytime that there's a hot water demand inside the house, the water heater will switch on and heat the water to the appropriate temperature, basically as it flows through the appliance. There's an extremely high-powered burner inside the appliance that is able to meet the temperature rise and water flow demand for as the water is flowing through the appliance, and immediately heats it to the appropriate temperature and sends it back into the house. And tankless water heaters have earned this reputation of being the green alternative to storage water heaters. And it's true that they're much more efficient at heating the water than the storage water heater, as we saw from Brian's slides earlier. But the other thing to think about too with the tankless water heaters is that they don't have the standby loss energy from the water sitting around in the tank, especially if they're not used very much. If the water is sitting around for hours or days at a time in a storage water heater, you can get some heat loss between the tank and the outside, which could be reduced with more insulation. But this is not an issue at all with tankless water heaters, because there's no, in most cases, there's no tank of water that's sitting around. Although some will have a small 1 to 2 gallon tank that you can somehow that you can attach to the system to help meet some of the high demand of the water flow. But anyway, today I want to talk mainly about the methane emissions. So methane is the principal component of natural gas, which is the fuel that's used to heat these water heaters. And there are also propane versions of these appliances, but we do not measure these. The propane versions would be used in the more rural areas where there's not access to piped natural gas from the distribution system. But the component, or the way that the appliances would work for propane water heaters would be very similar. We're not as concerned about propane emissions into the atmosphere, though, because unburned propane is not a greenhouse gas, unlike methane. Although the CO2 emissions from burning the methane and propane would be comparable for the two different types of appliances. But here we're mainly interested in understanding the additional climate impact of the leaked methane from the appliance itself, which before the study had been poorly quantified. So here's a picture of how we took our measurements. I'll talk about the direct capture method that we came up with for measuring the emissions from the appliance. But basically, this black tube here is a calibrated fan that will measure the airflow through the fan, and we can put it right at the exhaust of the different appliances. As you can see, here's a tankless water heater emitting into this fan, and then this is on top of someone's roof where the exhaust from a storage water heater would be emitted. And we can direct those emissions through this fan, and then through the understanding the rise in methane concentrations compared to the background measurements, and knowing the airflow through the fan, we'll understand how much methane is being emitted from the appliance. And we can do this from the appliance while it's off, while it's on, and while it's turning on and off. Here's a picture of the analyzer that was used for the method. It's a Picaro cavity ring down spectrometer, and it's able to measure methane and carbon dioxide in real time. So the methane and carbon dioxide is able to be measured at least the methane is able to be measured at parts per billion accuracy, which is necessary for this method to really understand those small changes in methane concentration that you get after diluting the emissions from the appliance through this high-powered fan. So here's a typical plot that we might see from a water heater while testing it. So as you can see, it starts off, the dotted horizontal line here is what we measured to be the background methane concentration. And then the black trace is the concentrations that we were measuring in the fan while directed at the exhaust from the water heater. So before we even turn the appliance on, you can see that there's an amount of emissions that are happening, what we're calling steady state off emissions. So the appliance is not even being used, and you can see that the concentration of methane is higher than the background concentration of methane that we measured away from the appliance. And then we turn the appliance on, and you can see that there's this other steady state on period where the methane emissions are even higher than they were while they were off. And that's not the case for every water heater, but for this particular one, we did find that it does emit more methane while it was on than while it was off. And also we have this on pulse, which happens when you turn on the appliance. And this is uncombusted methane that is emitted while the appliance is turning from off to on. Likely to be due to when the burner is firing up, that not all of the gas gets burned right away, and emits some amount of gas as unburned methane as it's turning on. And similarly, when you turn the water off, which we did here, there's another pulse of methane that we get. And this is also could be due to a number of things, which could be like as the appliance is turning off, that there's a amount of a gas that's escapes after the burner is extinguished, and it creates this off pulse of methane. And then it returns back to this steady state off baseline period until it's turned on again.
Hey, Eric, quick clarifying question. Is this representative of both storage and tankless water heaters, or is one or the other?
Yeah. So the magnitudes of the heights of the peaks and the amounts of steady state emissions will be different for tankless and storage water heaters, but the general shape of the trend is similar for both. As we'll find out later, we found that there was more steady state off emissions for storage water heaters than tankless water heaters, but the steady state on, for instance, was generally higher for tankless than storage water heaters. But in general, this is the general shape of what we're measuring during these measurement campaigns. So now just to show what we found for when quantifying the total amount of emissions, while the appliance is on, so steady state on emissions, we found that the tankless water heaters were, as I just mentioned, were quite a lot higher than the storage water heaters. In fact, the storage water heaters were very close to zero in most cases. And in some cases, we actually found that the storage water heaters were methane consumers, meaning that they were possibly even consuming, background methane in their flame while they were burning. But that wasn't the case as much for the tankless water heaters, as you could see. Nearly everyone had a positive emission rate while it was on, and it was generally quite a lot higher than the storage water heaters.
So basically, Eric, so this is saying that the tankless ones aren't completely burning the methane.
That's right.
During use,
this would be incomplete combustion, I would call it. Because it's running, and it is burning most of the gas. This is still a very small amount of the gas that's not being burned while it's running, but some of it is escaping as unburned methane during that time. And we'll attribute that to incomplete combustion at this point. Steady state off, however, would not be incomplete combustion because there's no combustion happening in the first place. So this would be more of a leak. With the exception of storage water heaters, many of these that we measured had pilot lights. So it is possible that the off emissions from storage water heaters could be attributed to the pilot lights in the appliance. But however, tankless water heaters do not have pilot lights, and nearly everyone that we measured, and I think that they're required to be built like this, is that they have the electronic ignition that will electronically ignite the flame when the water heater switches on. But in general, the storage water heaters emitted more methane during the off periods than the tankless water heaters. And then for the pulses, we found that the tankless water heaters had much higher pulses than the storage water heaters. As you can see here, that they're several times higher for the tankless water heaters for both the on and the off pulse compared to the storage water heater. And the spread of this plot too also shows that nearly every tankless water heater had these high amounts of pulses. There were very few that had little to no pulses of gas while they were switching from on to off and off to on. So the other component of this is understanding how often a water heater is used on a typical day. So we measured this ourselves from about a couple dozen appliances for each tankless and storage water heaters. And what we found is that by measuring how often an appliance comes on per day and at what times it comes on, for how long it comes on, we found that the total amount of time that the storage and tankless water heaters came on per day was fairly similar between the two different types of appliances, which makes sense, considering that if someone is trying to use their appliance the same amount per day, that the burner is going to need to be on for a similar amount of time to heat that same amount of water. But however, the tankless water heaters, in terms of the number of times they came on per day, exceeded that of the storage water heaters by about 10 times. We found that the tankless water heaters on average came on about 30 times per day, while the storage water heaters only ignited their burner about 3 times per day, which is important for the tankless water heater because I just said the amount they have such high amounts of emissions while they're switching from on to off and off to on. And even while they're on, there's that higher amounts of methane emission rates from the incomplete combustion. Interestingly, we also measured the length of the individual draws, and the x-axis here shows the length of a draw, and then the height of the bar shows the frequency of that bar, or of how often the water heaters would come on for that amount of time. So as you can see, the tankless water heaters, most of the draws from the tankless water heaters were less than 1 minute. In fact, the vast majority were less than 1 minute. But on the flip side, storage water heaters, when they come on nearly every time for many minutes. Almost none of them came on less than 1 minute, and most of the time they came on for 5 to 10 or more minutes. And this is also important just because, as we said before, the methane emissions from tankless water heaters while they're turning on and off is so high that if they're coming on for such a small period of time, that we're going to get those methane emissions during that time, even if they come on for less than a minute. Another part of the measurements that we took was we measured a few kitchen sinks where the faucet had a single handle, kind of like the picture here. And you can imagine if you have a sink like this, that you can set the temperature based on what angle you put your faucet at. So either be all the way to one side for hot or all the way to the other side for cold. And interestingly, what we found was that we wanted to know what angles would trigger the water heater when you turn it on all the way. So if you imagine this side of the plot would be all the way towards hot, and this side would be all the way towards cold. And then this would be, however high the dot is how frequently that water heater would be triggered. And this is only for tankless water heaters. So you can find that if you were to put the handle exactly in the middle between the hot and the cold and turn it on all the way, at all the sinks that we measured, that was enough hot water draw to trigger the tankless water heater to go through its on-off cycle and supply hot water to the faucet. And so the interesting thing here to think about too is that there's also a behavioral side of this too, where people sometimes maybe only are trying to wash their hands or just quickly turn the water on and off to rinse something off. And if that handle is 50% or more towards the hot end of the faucet, it's going to trigger the hot water heater for the hot water. And if it's only on for a couple seconds, you're probably not even get the hot water to your sink. Or maybe you don't even want the hot water in the first place. So there's definitely that behavioral component as well, with trying to understand how many of these draws are because people actually want the hot water and they get it at the sink, or it's just because they are trying to or because they inadvertently triggered the hot water heater when they didn't want it in the first place. So now I just wanted to talk a bit about the overall emissions from the water heaters and how this scales up. So we have we measured the emission rates from the different appliances from the different periods of use, and we measured that usage rate. So what we did is we paired all of our different data points of methane emission rates and the different data points of usage rates to understand how these combine together to understand how much methane is emitted from a typical appliance under different various usage patterns. And what we found is that the storage water heaters, most of the emissions from the storage water heaters by far come from when they're off. And that's because, as I mentioned before, they sit off most of the time per day, and that's where most of the emissions come from. They have a higher rate of emissions while they're off than tankless water heaters. And the emissions while they're switching on and off and while they're on are relatively low in the first place. So that's why most of the methane emissions from storage water heaters are emitted while they're off. But on the flip side, tankless water heaters have a very different story. Most of their emissions, nearly 50% of them, come from the periods while they're turning on and off. And that's in part because I mentioned earlier that they turn on and off, at least from what we measure, on average 30 times per day. And some of those times may be inadvertent switches on and off in the first place. And the other 25% comes from steady state off emissions. So this is when the appliance is off. And the other 25% comes from this steady state on emissions. So that's when the appliance is on, and that would be incomplete combustion from the appliance. So as I said, this is just CH4 or methane emissions, and we want to compare it to how this would compare to the carbon dioxide emissions. So what we can do for that is to take these methane emissions and convert it to carbon dioxide equivalents. For this, we use what we call the global warming potential of methane. And in a 20-year timescale, scientists have figured out that methane is approximately 80 times stronger of a greenhouse gas than carbon dioxide, just because it's better at trapping heat in the atmosphere. So we can convert these methane emissions now to what we call carbon dioxide equivalents, and compare that to the amount of carbon dioxide that we expect each of these appliances would emit. And as I said before, the storage water heaters are generally less efficient than tankless water heaters. So they'll emit more carbon dioxide than tankless water heaters. And by the calculations I did, I found that the carbon dioxide emissions from tankless water heaters is in fact less than storage water heaters, but the methane emissions are more than storage water heaters. But those methane emissions are not enough at this time, or by these calculations, to offset the savings in carbon dioxide emissions that you get from the higher efficiency of the tankless water heater. And again, these are only just comparing gas appliances. We could talk more about later about the electric alternatives, but there are no on-site methane emissions from the tankless water heater or from electric appliances. And also with the gas appliances, it's also important to note that these methane emissions are only coming from the site of the appliance itself, meaning that there are, as I mentioned before, we know that there's methane emissions upstream of the appliance as well. Methane is emitted from urban distribution systems. We get methane from leaking from distribution systems underneath city streets, from production, from transmission, and all of that is in part to to produce and distribute the natural gas that your appliance is using in the first place. So this is all additive to those other methane emissions that we know exist upstream of the actual usage point of the gas at the appliance itself.
So Eric, just this is such a great slide. So basically what we're seeing here is that if you were just to compare the combustion, you know, the CO2 from combustion, the tankless would look pretty dramatically lower than the storage. But when you add the methane leakage in, it starts to make them more equal there. Exactly. But still the tankless is less overall. I'm just kind of recapping what you said, because I think this is such an important part of the presentation right here.
Right. And it also a lot has to do with the usage patterns too, because if you imagine, like, if someone has a tankless water heater in their vacation home, for instance, compared to a storage water heater, these turn on and off periods and steady state on periods are going to be a lot lower because their appliance is not being used as much during the day. But meanwhile, if you're using your appliance a lot, like if it's on a lot, then actually the storage water heater, the methane emissions are not really going to change that much. In fact, they might be lower if it comes on more often per day, because the total amount of methane from a storage water heater is mostly emitted while it's off compared to a tankless water heater. Yeah, that would also be a way to change the ratio of the methane emissions between the tankless and the storage water heaters, depending on your personal usage scenarios, if you're a heavy water user or a lighter water user. Oops. So as this is the last slide here, which is just some conclusions from our study. We found that tankless water heaters emit more methane than storage water heaters overall, particularly through turning on and off, as we just talked about. And then the storage water heaters emit most methane through steady state off emissions, which is believed to be incomplete combustion of the pilot light in our scenario, because most of the measurements we took of storage water heaters were units that had pilot lights. And we found that total methane emissions from water heaters overall is about 0.4% of the gas they use. And as I mentioned before, that's additive to the methane emissions that we know happens upstream. And trying to keep that number as low as possible is really important to reduce the overall net benefits of the lower carbon intensity of using natural gas over, say, dirtier energy sources like coal. Just want to acknowledge my co-authors in the paper. PI from our lab was Rob Jackson. And then we had Colin and Harmony and Simone helped out with this work as well. And this is all done while I was a grad student at Stanford doing my PhD. And the paper was published in early 2020. So that's the end of my slides. Thank you. And if we want to switch over to questions at this time,
Yeah, we had a couple of good questions. One, just I want to acknowledge that there's a question about the upstream distribution leakage, and I think in the slide you showed, and this was the EPA number, I believe, is 1.5% of methane. Total methane is leaked in the atmosphere, and I know that there's a lot of work going on about getting better measurements for that number. And I've seen things that they're much higher than that as estimates. What's your point of view about that? Like I've noticed that I think I saw something recently that even in the Permian Basin, there's measurements as high as 9%.
9%, yep. Yep, exactly. Generally the EPA's estimates are lower than what's published in the peer review papers. And that's been pretty consistent, especially recently with the work that's come out. I know that a lot of people who have taken those peer review papers and tried to distill them, it's a really hard question to understand how much methane is emitted from natural gas. But the general consensus is that it's probably closer to 3 or 4% overall. And again, this is also now adding in our 0.4% just at the end use itself, and doesn't include any of these other processes to get the natural gas produced and to your home in the first place.
Right. And that 0.4 is just from water heaters. So
just from the water heaters.
If you imagine that there's some amount of leakage from all the other gas devices we have, which is, and I know you've done some research on that, it seems like most likely all of the gas devices are contributing some leakage in our homes, correct?
Yeah, we also did a paper on gas stoves, and for that one we found that the methane emissions were closer to 1% of the gas that they burned. But again, remember that gas stoves don't use much methane in the first place. So the overall, the total amounts of methane emissions from gas stoves were lower than water heaters by about 3 times lower for total emissions per appliance.
Great, Eric, thanks so much. We have a couple questions on if an electronic ignition water heaters would change any of the study's conclusions.
Yeah, we didn't measure any of the electronic. There may have been there were mostly pilot lights. There may have been one that we measured for the storage water heaters, but the idea is that it's possible that would reduce the steady state off emissions. If in fact these emissions are coming from pilot lights, then switching to an electronic ignition for the storage water heaters would in theory reduce this bar. However, it probably wouldn't go to 0, because as you can see with the tankless water heaters, even though they have electronic ignitions, there's still some amount of steady state off emissions from the tankless water heaters. And that could be due to just general leaks from the appliance. We know we've seen this with the stoves as well, and with other appliances, that the gas can be leaked from, misfit connection between the appliance and the gas supply, or from a faulty valve within the appliance, for instance. That could be an idea of where the gas is coming from. We've never actually investigated what the manufacturer reason is for these leaks in the first place, just because a lot of the times all these measurements that we've taken have been at people's homes, and we're not going to rip apart their appliance to understand where these emissions are coming from. But we wanted to get an understanding of, in the real world, what are emissions from appliances in actual people's homes that use these appliances on a regular basis.
Is there any other kind of like quality of storage water heater or a tankless one that would change these numbers? Like, I mean, is there different types of burners or anything like that? Or is it really the main difference, the ignition system?
We don't really know. Yeah, we don't. We didn't have enough samples to really understand those differences. We did look at the difference between condensing and non-condensing units, and there really wasn't. I don't recall there being any sort of major difference between the emissions between those two different types. But that's definitely an area of future research that we'd like to do, is to try and better understand these differences in different burner types and ignition sources with a larger data set.
Right.
And especially in other regions too, because again, we took all these measurements in California, and I think that just understanding if the water heaters are different in parts of the country, and just understand how the emissions would change there as well.
Right. How about recirculating, water heater systems and pumps? Were they part of the study at all?
Yes, there were a couple of the usage data that had recirculating pumps, which we took note of, and for those, that makes the most difference, as you can imagine, with the tankless water heaters, because every time that recirculating pump comes on, you're also going to get a cycle of the tankless water heater. People have lots of different systems of recirculation, as you can imagine. There could be, the motion activated button press in the shower to get this water circulating before you get in the shower system, to people who have it on a timer that just comes on at high usage points of the day. But the recirculating would, you can imagine it's basically like turning the water heater on, or using, or as a draw of water anytime that pump comes on. So anytime that it comes on for a tankless water heater, that makes it go through the cycle. And for the storage water heater, it won't necessarily make it go through the cycle, but it will reduce the hot water content of the tank.
Eric, what about other pollutants? So we've been talking about methane, and I know you've done some other studies around other pollutants, but in this study, did you measure any other pollutants besides methane? Like we've heard a lot about these factors, these different chemicals that are embedded in the natural gas, like benzene and formaldehyde and other things. Any other information like that you have? Yeah,
that's a great question. The thing to think about with the water heaters. So first of all, no, we did not measure anything else for this study besides methane. So the thing to think about with these water heaters is that, unlike your gas stove, they're usually not in the space of your house that you live, right? Most people's water heaters are either in their garage or their basement or outside, or in a closet inside their house. And unlike your gas stove, these are required to be vented outside. So you can imagine that while they're running, that as long as your vent is working properly, that all the byproducts of combustion, including those other pollutants that you would get from burning the appliance, or the combustion in the appliance, will immediately go outside and won't enter your house at all. That's in theory how that should work. And that's not how that should work with the gas stove, because we've talked about, it's in your kitchen and it has to be, the vent is not 100% effective, but that's not necessarily the case with these water heaters. But what we do know is that, as you said, we have done a study looking at the gas composition of unburned gas. So if your appliance is in your house, like in a closet, for instance, in your house, I know some people have their water heaters, in an interior closet, for instance, or in their basement. If there is a gas leak between the gas supply and your appliance, it is possible that you would be getting some of those other chemicals that we found in unburned gas emitted into your house. So, for instance, we found that gas regularly in California, at least, in Boston, and the studies that we published so far, contains chemicals like benzene and other hazardous air pollutants that could be emitted alongside the natural gas if you have a gas leak from the appliance in your house. But as I said before, the byproducts of combustion, so that would be the NOx, for instance, NOx or carbon monoxide, those are the two of the most common byproducts of combustion that you get from either incomplete combustion, or NOx is just the oxidation of nitrogen from the high heat of the burner. We didn't measure it directly from these appliances, but it's pretty well known that most combustion processes will emit some amount of NOx. But again, that's going to be vented out of your house and through the venting process of the appliance, just like the other byproducts of combustion would be.
Right. There are some questions about sample size too. I think you mentioned a couple dozen of each of these types. Is that right?
Yeah, I believe it was for the loggers, we visited over 60 homes in total, and then split that up into there were about a couple dozen of the loggers. I think it was 23 each. And I believe it was 16 and 17 samples of tankless and storage water heaters.
Great.
For the methane emissions.
So Brian is wondering, it sounds like the 0.4% methane leakage is on a per device basis. Do you have a sense of how that adds up in aggregate? We talked about this a little bit across the deployed tankless gas appliance base, and how that compares to upstream leakage.
Yeah, so the 0.4% would kind of fit in with this here. And this would be just for water heaters. And you can imagine that all these other possible sources of methane leakage are all in part to service that water heater and all your other gas appliances in your house. The 0.4% is the aggregate estimate for total amount of emissions for gas fired water heaters. The total amount of so that's taking into account the estimated amount of gas that a typical water heater would use in a given year, and how much of that gas would be emitted as unburned methane. And so in aggregate, that would be about 0.4% of the gas that it uses in a year would be emitted as unburned methane.
So then, I mean, if using this 1.5 number from EPA, you'd say then for water heaters, 1.9% of their estimated gas usage would be unburned methane.
Right. If we're taking the 1.5%, and as we mentioned earlier, that's probably quite low compared to other peer review papers that have come out looking at similar methane leaks from upstream natural gas.
Great.
Brian, should we just go into
let's talk about let's look at some other comparisons here.
We'll be back for a couple of other questions at the end with Dr. LaBelle, but we did want to not just leave you with, hey, instant water heaters leak a lot of methane. We wanted to leave you with good, hopeful news on water heaters you should be considering that don't leak methane.
Well, this may be just also some just general information to help you understand better how these devices compare. And of course, this is really hard to do because for any one of these categories of devices, obviously there's a whole host of options available at retail. And so what we've done here is just pick a few what we consider good representative options. So this is a typical electric storage tank. Their performance doesn't change that much. Electric tankless can change quite dramatically on how big a one you have, but we tried to pick one that's equivalent in size to what a home that uses a 50-gallon storage tank would need. And we picked a pretty efficient and Energy Star gas storage water heater. Most of the gas storage water heaters out there are not anywhere near this efficient, but we picked a pretty high efficiency one just for comparison. And then a good gas tankless one, again, pretty efficient one. They're not all this efficient at all. And then the electric heat pump, these are pretty consistent in terms of their efficiency levels. So this one is pretty easy to choose. But those are the kind of 5 basic technology options. And if you looked at just the cost to purchase the device in the first place, there's obviously quite a range of cost differences. The electric tankless are cheapest. Electric storage are also quite cheap. A cheap gas storage would be maybe more like $700 or $800, but it wouldn't be anywhere near this efficient. And then, gas tankless gets more expensive. The electric heat pump ones are typically some of the most expensive ones out there if you look at the initial retail costs, but there's really good rebates and other incentives available here in Oregon. You can get one of these devices for about $900. So it becomes, really cost effective in terms of the upfront cost. And of course, installation, that's a whole nother thing. And that's going to depend really a lot on your individual home. So we're not going to talk so much about that. But for the most part, if you're going electric to electric, it's pretty straightforward. Gas to gas is pretty straightforward. As soon as you go from gas to electric, it gets more expensive, and it would be the same if you had an electric one and were putting in gas, that would be more expensive. But anyway, so that gives you a kind of an idea about the upfront cost of the devices. And then, you know, the government puts these little yellow labels on each device that gives you at least a pretty decent idea. I consider a relatively good apples to apples comparison about the cost to operate them over a year. So you can see the electric ones are the most expensive, almost $500 for an electric storage one. Typically, the electric tankless one is going to be slightly better. Gas typically is going to be lower cost to operate than those electric devices, which is part of the reason why they're so popular. But then if you look at the electric heat pump ones, they really blow everything else away in terms of cost of operation. And of course, this will depend, these comparisons will differ based on the relative cost of electricity and gas in your region, and that changes a lot. These are national average numbers, but you can see that the electric heat pump ones are by far the lowest cost to operate of any of these devices, including the gas tankless, which we were just talking about. And then if you look at if you take that information from that yellow label, because it has on it the number of therms that you would expect to burn or the number of kilowatts you would expect to consume, and you convert those numbers to carbon emissions, and this is using Oregon electricity and gas values. This will change a little bit from region to region, but not a lot, but a little bit. You can see again that the electric heat pump just blows everything else away in terms of the carbon emissions. And from what we were just seeing from Eric's presentation, I think it's fair to say that this gas tankless total emissions are quite dramatically underrepresentative of what's really happening because of that methane emission from unburned or leaking methane. So you can see that, again, this is going to vary from place to place, but I think it's fair to say anywhere in the country, an electric heat pump would produce far fewer carbon emissions than any other device. Okay, so Joe, why don't you tell us a little bit about the story with sales?
Right, far fewer carbon emissions and no methane leakage as well to get to today's subject. Yeah, so this chart shows the sales of heat pump water heaters in around their first decade of existence. I think a lot of us are excited about this technology. It's been around a little bit longer than a decade, but these are Energy Star's numbers tracking their growth. And the compound annual growth rate is around 17%, which is pretty good. It tracks kind of wind and solar, but we're starting at a very small amount. So we went from 23,000 to 112,000 for heat pump water heaters. But as we showed before, gas tankless is almost 7 times that in sales. So heat pump water heaters have a ways to go, and gas tankless sales are still growing. And then if you zoom out even one other level, these are both still relatively drops in the bucket compared to the gas storage and electric storage water heaters, which are almost at half, 50% of the market each. And in the millions. So lots of work and education to do around selling the benefits of heat pump water heaters. But we are seeing some growth of heat pump water heaters so far.
Actually, Joe, I mean, just comment here in the Northwest, the electric heat pump water heaters have been promoted pretty heavily. So the market share numbers here in the Northwest are much higher than this, yeah?
Right. Yeah. This is the national average of the 1.1%. But in the Northwest or in states like Maine and Vermont, the Northwest, we're seeing about 20% adoption rate of heat pump water heaters. In Maine, it's close to 50%. So there are markets where this is really moving quickly, and they're showing us what the future could look like.
All right. Well, let's talk about what's coming. Joe's a heat pump water heater geek, water heater geek in general. So tell us a little bit about what you see.
I'll tell you a little bit about why. But I just wanted to say I did a review of there's a couple of major manufacturers of heat pump water heaters on the market today, and some new ones to celebrate are this. Nobody really thinks that everybody's excited about the latest electric vehicle. Well, let's start getting excited about the latest heat pump water heater. This is the A.O. Smith Voltex AL. It just came out late last year. I wrote an article in Clean Technica reviewing it. I'll put it in the chat in a second. But really excited. the quietest heat pump water heater. For those of you who have a heat pump water heater out there, there is some noise from the fans, but they're down to about, they got it down to about 45 decibels, which is like a quiet dishwasher. So really silent. It has an amazing a UEF, which is the efficiency 3.8. Again, we were looking at other water heaters don't get above 1. And it's got water connections on both the top and the side, so it's a zero clearance. You can kind of put it anywhere. So really excited about the new A.O. Smith, and I'll put my review of that water heater. And then other water heaters to celebrate, of course, the Rheem Proterra plugin. This came out last year in August, and I wrote an article on this one as well. This is exciting because you can see it on the picture. It's a plug-in water heater. You can plug it into any 110 volt outlet. And it will produce all the hot water you need. It has a couple tricks up its sleeve, and I won't get into all of those, but this is just hitting the market. We're doing some field studies on this, and they're showing real immense satisfaction with these water heaters. So this is a great gas replacement water heater. A lot of times, if you have a gas water heater, you don't have 240 volts of electricity right there where your water heater is located, but you probably have an outlet, and so you can plug this water heater right into that outlet, which is great.
And this one needs a dedicated circuit, right? So you couldn't. This would have to be a circuit that just goes to your water heater.
Right. Thanks for this is they have 2 versions. The Rheem has 2 versions. The dedicated circuit one, which has a stronger compressor, so you do need a dedicated circuit for that. And there is also a shared circuit heat pump water, 120 volt heat pump water heater that can be on the same circuit as other appliances. You don't want an appliance that has a lot of draw, but it can be on the same circuit as many appliances. So this one, you can see again, it has a great efficiency rating. It has these plug-in water heaters have a little lower first hour rating. That's how much first hot water you get in the first hour than the 240 volt versions, but still pretty good ratings there. So those are both really exciting water heaters. And then we're excited about other manufacturers that are getting into the market. LG, GE, we're expecting water heaters from these 2 manufacturers soon. And there are other versions like split systems where the condenser is outside and the tank is inside. And so there's lots of versions of heat pump water heaters and more every year.
So those split systems tend to be more expensive, isn't that correct? I mean, that's really it's a cool idea. I love it, but they tend to be more expensive in general. Yes, they do.
The split systems do tend to be a bit more expensive than these tanked units. But they do, if you have a difficult application where a split system is the best option, then it's usually worth the cost. Because remember, with heat pump water heaters, they usually pay for themselves in anywhere from 2 to 5 years just by the savings, the energy savings, because they're so efficient. And okay, we said a huge geek on heat pump water heaters. I do from my day job with New Buildings Institute. I help project manage the Advanced Water Heating Initiative. I want to put a quick plug out there. This is an initiative where everyone is welcome and we're trying to focus on advanced water heating, which is heat pump water heating. And you can go to the next slide. Yeah, we are looking at all the barriers for heat pump water heaters and how do we overcome them. We have working groups on residential, commercial, equity, and connectivity. So if you're interested in water heating, we welcome you to join us. I'll put a link in the chat to the Advanced Water Heating Initiative, but we'd love to help your support, because as we've seen, in some markets we're ahead with a higher adoption rate, but we have a lot of work to do to convert water heating to advanced heat pump water heating. So that's a quick plug. And yeah, Brian, do you want to?
Yeah, just a reminder, that we have lots of information about if you're a homeowner and you're interested in information about installing any of these devices, go to our Take Action page on our website. You can see here in the middle, install a heat pump water heater. It gives you good directions on how to do that, even contractors to use here in the Oregon area. And then I wanted to also point out, we haven't talked about it today, but see this button down the right, the IRA incentives. If you click on that, you'll get a link to this fantastic calculator from Rewiring America, which shows the incentives available starting this year. Tax incentives, we don't have information about the low income incentives here, but you can see, like, if you on the heat pump water here, there's $2,000 up to $2,000 depending on your tax bracket of savings available in terms of tax credits, basically for installing a heat pump water heater. So, you know, back to all those costs we were talking about, there's real advantages to taking a look at what you can save from the incentives. So that's it. Thank you very much. We really appreciate you tuning in today. And I think, is there any other questions we want to try to address, or do you think we covered it all?
Eric, did you see any questions in the Q&A that we should touch on? We did answer
just a quick clarifying is that I don't actually work for an energy company. I guess PSE is a name of energy company in the Pacific Northwest, but I work for a PSE Healthy Energy as a nonprofit science and policy research institute based in Oakland, California, where I work currently.
Yeah, there was a little confusion
slides,
about
I apologize.
We got a lot of PSE lovers and haters up here in the Northwest, depending on
you're not working
for
the energy company.
Yeah.
Yeah. But yeah, we have a lot of really interesting research coming out too, and has come out recently. So
tell us about some of the things you're excited about that you're working on.
Yeah, so as I mentioned before, we've been doing a lot of gas composition research, trying to understand like what's in gas besides methane. Been doing that all in different parts of the U.S. and then internationally, and then also working on measuring other appliances for methane and other hazardous air pollutant emissions as well.
Thanks so much. Yeah, Eric, that's fantastic. You're leading the way to understand, you know, what happens when we combust methane in our homes. So we really appreciate all your work. And thanks for being on your second webinar, one of our rare repeat panelists. It's always such a great pleasure to have you on, and we look forward to having you on other ones as you're producing more great science.
Yeah.
Thank you very much. Thanks for having me again.
Yeah, really appreciate it. Really appreciate it. Hey, maybe there was one question here that I reminded me of something I forgot to say, and that we should always remind people about, is that when we're talking about emissions, you know, and we gave you some carbon emissions, we gave you some comparison of these different technologies in terms of their carbon emission profiles. I forgot to say it, I should have said, and someone reminded me here that, you know, that is all just based on the current electric grid mix that's available. And as everyone here on this call knows, the grid is getting cleaner literally every second as more green energy, renewable energy sources of generation are added, whether that's rooftop solar in one person's home, or these giant new wind farms that are going up all over the place, or solar storage, solar energy collection and storage systems are going all over. So our grid is getting cleaner all the time. So the point is that here in Oregon, for example, we have laws mandating 100% clean energy by 2040. So we will have the emissions from any electric device will continue to go down, down, and down. And that just is not the case with the gas devices. So wanted to thank you for pointing that out. And yeah, always a good thing to remind ourselves of when we're talking about these comparisons.
Perfect. Well, thank you so much, Eric. Thanks for being on. Thanks everyone for listening in today. Huge thanks, Brian. And give us our closing line, Brian.
Yeah, well, we appreciate everyone tuning in, and good luck with all your electrification projects out there. We really want to support you in your own work to reduce your carbon emissions. So reach out to us if you have any questions about that. If we can help you, we will. And if we can't, we can direct you to someone who knows the answer. So thanks very much. And we hope to see you at one of our upcoming webinars soon.
Thanks, everybody.
Thanks, everybody.
Bye-bye.